So I think you voted for this talk, and you wanted to hear about functional programming. So do you know what functional programming is if you voted for functional programming? Who knows what functional programming is? Okay. So functional programming is very different from imperative programming. In imperative programming, you specify instructions that manipulate state in order to achieve a goal. And this is how C and C++ work. You have statements manipulate variables, and in the end, you will have set up the memory in such a way that it contains the result or a segmentation fault. And C and C++ work this way because this is how the CPU works. And they're close to the CPU. In the CPU, you get assembly instructions that manipulate memory in such a way that you get the result. So this is how C and C++ work. And this is also how like an IKEA manual works. You have a sequence of steps that you need to do in order to assemble your piece of furniture. In contrast, we have declarative programming. In declarative programming, you specify only the outcome, only what you want. And then there is some sort of smart system that figures out how to achieve this outcome. And this is how Haskell or Prolog work, for example, for programming languages. This is also how formal grammar works. So in a formal grammar, you specify productions, and they describe what is valid, like what makes valid text, but they don't tell you how to parse this text. This is the process. Then you need like a separate parser generator that generates actual code that will parse your thing. You merely describe what's valid. This is also how a thermostat works. You simply specify the target temperature, and then some system will figure out how to turn on the heating or the cooling in order to achieve this temperature. For a more recent example for me, this is how the DB booking system works. You specify where you are and where you want to go, and then they will get you a ticket, and they will get you to the destination. And sometimes this involves a taxi ride from Augsburg to Augsburg Central Station. So that's surprising, but in the end, you'll get there. Now, functional programming is declarative programming by composing functions. This is where the function is in. So it's declarative, but you compose functions. And this is the only slide that will contain Haskell code, don't worry. So this is a function in Haskell that computes the faculty. It takes an integer and it returns an integer, and we specify sort of rules. We say that the faculty of 0 is 1, and the faculty of n is n times the faculty of n minus 1. This closely matches the mathematical definition. And there is no temporal ordering between those rules. We can put those 3 lines anywhere in the source code in any order. They simply declaratively describe what the rules are. This is a sort function. It takes a list of integers and returns a list of integers. And we say that the empty list is already sorted. And to sort a list consisting of one element followed by arbitrarily many elements. I see a bunch of movement in the back. Sorry about that. We say that we take all the elements on the left. Then we add the first element and then all the elements on the right, where the elements on the left are all elements less than x, and the elements on the right are all elements greater than x. And this is a very declarative way to describe some sort of quicksort. It's like not really quicksort because quicksort is in place, and this is very much not in place, but it like declaratively describes how to sort a list, simply by following these rules. Now, why do we use functional programming? And functional programming is really nice because functional programming eliminates state. And that's nice because this is where all your bugs is. Like if you don't have state, you don't have any bugs due to invalid states or broken invariants. Some variable still contains the old value, but some other variable already contains the new one. If you don't have any state, you don't have any of those bugs. Oh, we're getting a second screen. Oh, nice. Okay. You also don't have any bugs due to like complex interleaved object references. Like at work, we do a plugin for PowerPoint. This is LaTeX though, and we essentially manipulate PowerPoint slides using this like complex DOM for PowerPoint slides. And this is like a class hierarchy with a bunch of reference counting, and then in the destructor of one thing, we have to make sure that we remove it from the parent first before we delete it, because otherwise it will recursively try to, and all of this stuff, right? If you don't have any state, you don't have any of that. And this is more relevant now than ever. If you don't have state, you don't have shared state, and this makes it trivial to parallelize, right? Because you don't have any shared state, you don't have any race conditions, and you can just split your work up into multiple threads or on a GPU or whatever and have it run in parallel. Now, functional programming is so great. Why is this the C++ meetup and not like the Haskell meetup, right? And the problem is that functional programming fundamentally does not map neatly to hardware. This is simply not the way the CPU works. So we will always have some penalty there. It makes it harder to optimize because the system has to translate the functional programming into imperative code. And in some cases, a human can do that better. So there is some friction in there. It's harder to use native tools like debuggers or profilers that are designed on the CPU level. They have to be like adapted to be functional. And while I want, for at least why we at work don't use a pure functional programming language, it makes it harder to interact with native libraries and OS APIs. Simply because it's functional, it's like a different universe. So whether you should use functional programming to solve a problem or not, or like a pure functional programming language is an engineering trade-off, right? You have to set up the pros and cons and figure out whether you want to do that. But we are doing C++, and C++ isn't a pure functional language. So we don't need to use functional programming for everything. We can only use functional programming to solve specific subproblems where it makes sense. And for that, the insight is that functional programming is all about composition. This is really the key. It's about composition. So to use it in C++, you write building blocks using efficient, optimized, and well-tested C++ code, and then you compose those building blocks using functional paradigms. And that gives you the best of both worlds. You've got the performance because the low-level building blocks are very efficient, imperative style, and then at the high level, you've got like very easy composition of those building blocks. So in this talk, I'm going to look at 3 topics. I'm going to spend about half of the talk looking at composition of algorithms, because this is really where it's like very applicable and where you can get a lot of gains. Then we will take a step back and look at like composing functions in general. And finally, we will look at composing I/O and see how it can be used there. So let's begin by composing algorithms. So I've brought a couple of lead code problems, and I'm going to solve them in an imperative style and in a functional programming style, and then we can take some insights. So this is a very simple one. Our input is a non-empty list of integers, and the output should be the biggest magnitude of an odd integer in the list. So for example, if this is our input, then the output is 7, because -7 is like the biggest number, has the biggest magnitude and is odd, right? So the output is 7. And this is imperative code to do it, right? We loop over all the numbers, we keep track of the current candidate. For each number, we like compute the absolute value, check if it's odd, and if it's bigger than our existing candidate, we update it, and in the end, we return the candidate. And because this is non-empty, this all works out. And this is very straightforward imperative code. We specify exactly how we solve this problem. And we also have some state in there, and we have to make sure that the state is properly initialized, right? Otherwise, the entire thing sort of breaks apart. But you know, imperative code. And so to make it functional, the question is, what is the composition, right? What are the individual building blocks that we can use to solve this problem? And there are 3. So first, we need to like compute the magnitude of each number. Then we want to filter out all the even numbers and keep only the odd ones. And in the end, we want to find the maximum of the resulting list. And we can sort of apply those steps one at a time using the C++ algorithms in what I call eager composition. So first, we're going to transform the input range into the one of the absolute values by using the transform algorithm. This takes our range at input, and then we store them into like an intermediate container with the transformation function applied. So it applies the transformation function to each element in our range and stores them in the container. Then we filter out the even numbers, keep only the odd ones, but that we use copyIf. And this copies only the numbers over where the lambda is true, and in this case, if it is odd. And then in the end, we get the maximum, so we just call the max algorithm, and this will give us the maximum value of the list. And this is, in principle, the style that would be possible since C++ 98, but I'm using the new C++ 20 ranges. And the only real difference is, instead of calling like begin and end and passing it as an iterator pair, the new algorithm lives in namespace ranges. I've abbreviated that stdr just for slide purposes. And then we can just pass the entire range as once, right? So like the range can be some container or something. And then we can pass that as once and don't have to worry about the begin and end pairs everywhere. Saves a lot of typing. Now, this is eager composition, and it isn't really nice, right? Because we have to create all these intermediate containers. We compute all the intermediate results, even if unneeded. Here we actually do need all the intermediate results, but in later problems, as we'll see, we can often skip many computations if we don't do it eagerly. And we still have state, right? We've got all these intermediate containers, and we have to do stuff in the correct order and so on. So much better is to fully appreciate the new C++20 ranges by using views. A view is essentially a lazy range whose values are computed on demand. So when you create a view, when you compose a view, this does nothing. It merely describes how your data is about to be transformed. It's a very declarative thing. And only the actual iteration at the end, this will trigger the computation. And as you iterate over it, the views will execute one step at a time, give you the new value, and pass that on in the pipeline. And this really enables a very functional pipeline style without any manual state. And just for slide purposes, all the views are namespace.views, so I'm using stdv. And this is how it looks using views. So to compute the magnitude of each number, we use the transform view. It's just like the algorithm, but we sort of pipe the input into it and only specify the transformation. And this first statement, it does nothing. Right? It just creates an empty wrapper over the range, essentially, that remembers, like it stores the range and the lambda. Right? And simply describes, OK, when you iterate over it, you will apply this lambda to each element. Then in the second step, to filter out the even numbers, we use the filter view. And this is like the lazy copy-if version. Right? And we simply specify our predicate. And this will continue the pipeline by saying, hey, we only want the odd numbers. And again, this does nothing yet. Right? It simply composes the pipeline further. And then in the end, we still use the max algorithm. And this is where the actual work does. Because max actually has a loop. It actually iterates over things. And as it iterates, it will ask filter for the next value, which will ask transform for the next value, which will ask the range for the next value. And then the value flows to the pipeline and eventually reaches max. It might be skipped. It is transformed. And then we have max. And then all the max will just do whatever it takes to get the maximum value. And you might say, OK, we still have state in there. We've got like the two variables in there. But that's not really state. That's just simply labels we've given to parts of the pipeline. And the more idiomatic way is to write it all in line. Right? So we want to get the maximum of the range transformed with the absolute value function and then filtered out only the odd numbers. And then we pass that to max, and then we get a result. And this is the declarative functional composition style by using individual building blocks to solve the problem. Now, the takeaway here are like, first we've got this composition shape, given a range, give me some slightly different range. And for that, the two big views are transform. This applies a function to each element. In most other programming languages, it's called map, but in C++, map is a data structure, so we call it transform. And then we've got filter, and this keeps only the elements that satisfy a predicate. Similar views in that category, for example, take while or drop while, this like removes a suffix or prefix from a range, and a couple more in that category. They take a range and lazily give you a slightly different range. And then the composition shape, given a range, give me a derived value. This is where the algorithms come in. So max and min gives you like the maximum or minimum element, and there are like variants that give you the iterator instead, and so on. You can use the count algorithm to give you the number of elements that satisfy a predicate. If you just want to know whether all of satisfy a predicate, there's an algorithm for that and some variants. And then like the other common ones are like find and search if you want to find particular elements in the input range. Now for the second problem, now we're having two lists and a target number. And the output should be two integers, one from each list, whose sum is target. So if these are our two lists and the target is 12, then the output is the pair 4, 8, because 4 plus 8 equals 12. And this is the imperative code. So we are taking our two lists as input, we're iterating over them, we're checking whether the sum is target, and if so, we return it as a tuple. Otherwise, we return null up to indicate that we haven't found anything. And again, this is the imperative code. And to get the functional version, we have to ask ourselves, what is the composition? What are the individual building blocks? And here, the building blocks are, first give me all the pairs. And now I want to find a particular pair whose sum is target. And we're again going to solve that with views. So to generate all the pairs, we use the Cartesian product view. And the Cartesian product view gives you the Cartesian product of the input, which is essentially, in this case, all the pairs, one from each range. And again, this is lazy. Like, this line doesn't do anything. It doesn't allocate a quadratic amount of memory and store it somewhere. It simply describes, as you iterate over combinations, you will get each pair from each making up of the two ranges. And then to find a particular one, we use find. Right? We give it our combinations as input and say, hey, give me the pair P, whose first element are all possible values from the first range, second element are all possible values from the second range, and now we want to get the particular target, and then we just return that instead. And again, the findIf one is the one that does actual work. Right? It will iterate over it, and it will ask the Cartesian product to give it the next value, and the Cartesian product will lazily give you those values. Now, we write a lot of code like this at ThinkCell, and the findIf thing is kind of ugly. First, we're giving like a tuple, so we have to like manually unpack that in the lambda using get, which is like just really ugly. And then findIf gives you an iterator over the particular pair, but we want to get like the value as an optional. So we have to like manually unpack it in the end. And so at ThinkCell, we have like a custom range library with like custom algorithms. And so we've got like a custom find function that is much more convenient to use. And so the two changes are, first of all, the lambda. Instead of just taking the tuple, the lambda can take multiple arguments. And then when you invoke it with a tuple, it will automatically unpack the tuple and call them to the lambda. And that's just more convenient. Now we've got A from the first range and B from the second. And then we've got this like return value or none specifier. This specifies what kind of return type we want. Right? In this case, we want to get the actual value as an optional. So return value or none. We also have like return bool if you just want to know whether, and then like find essentially is a contains. There is like a return iterator, a return index or something, and we've got like a couple dozen of those template policies. And this just makes it more convenient. But for this talk, I'm going to stick with the standard version. Because one big advantage that the standard algorithm has, in the next standard, so in C++26, we will update the range algorithms with execution policies. So because this is like a quadratic algorithm, and so there's potentially a lot of data, and it's really easy to parallelize functional code. How easy it is? Well, it's just a matter of adding the execution policy. So you just change the call to the algorithm, give it an execution policy, and now the actual find will be split up into multiple threads and executed in parallel. And simply by partitioning the data in the appropriate way, we've enabled this sort of very simple transformation to do parallelization. And now we've got the speed up. Now, of course, the quadratic algorithm itself is like not very efficient. Like it's much better if you have some sort of lookup table. And this is where it really comes in. This isn't functional, but it's fine, right? We don't have to use function for every program. So here we're creating a lookup table using range and then using 2 to essentially create a container, and this creates an unordered set initialized from the range. And now we call findIf, iterating only over the second range, and check whether we have the matching element on the lookup table. And now it's like a linear time operation, but we require more space. So, but like if it's an interview question, this is usually the answer they want instead of the one. Now the composition shape here is the input is multiple ranges and the output is a single range. And we see in Cartesian product, and this gives you a tuple of all possible element combinations. And there's like a quadratic number of those. Then we also have zip. A zip gives you a tuple of like corresponding elements. So zip, the first gives you a range whose first entry is the tuple consisting the first entries of each subrange and then the second entries of each subrange and so on. So it like doesn't change the number of elements, but it gives you the pairwise. It iterates over multiple ones in parallel, so to speak. And this one is really useful, especially if you want to do like a zip of a range with like the range itself but slightly shifted, and then you've got like all adjacent elements, for example. This is often very useful. And finally, in C++26, I think we will have concat, and this gives you all the elements of all the ranges in order. So first, all elements from the first range, then all elements from the second range, then all from the third, and so on. So like a sum of all the possible elements. And those are the three big kinds on like where you combine multiple range into a single one. Now for the next problem, this is an interesting one. So the input is a list of integers, and as the output, you want the length of the longest contiguous subsequence of increasing numbers. What I mean by this is if this is our input list, then the output should be 4, because the subsequence 2, 4, 5, 7 is the longest subsequence of like increasing numbers. Right? And solving this imperatively is like really messy. Because we have to keep so much state in our head, right? We need to keep track of the maximum length we've seen so far, of the length of the current subsequence, and also the previous element to see whether it's like still part of the current subsequence. If so, we can increase the current length. Otherwise, we need to start a new subsequence by resetting the current length. and then we need to keep track of the previous one. And in the end, remember that the longest subsequence could be the last one. So the current length at the end might not be terminated yet, and it might be bigger than the maximum length. So you have to call max at the end there to make sure that you got this off by one condition. It's just a bit messy. Is what I could have said, but I just typed the name of the function and then GitHub Copilot gave me the body. So anyways, I guess in a way that's also declarative functional programming. So to do it properly, again, what is the composition? Well, we want to split the list into the increasing subsequences. Then we want to get the size of each one of those chunks, and then we want to return the maximum. So how do we do that? It's surprisingly short. So we start with our range, and then we pipe that into chunk by. Chunk by is a view that looks at pairs of adjacent elements and passes them to a predicate. And it gives you subranges split at the border where the predicate returns false. So it starts by asking whether 1 is less than 3 in this case. It is, so 1 and 3 are of the same subsequence. Then it asks for 3 and 2, but 3 is greater than 2, so we split the subsequence here, and the first element of the chunk by view is the subrange 1, 3. Then we start a new one beginning at 2. We keep adding elements as long as the current one is like less than the next one. Found the binary, and this is our second element. And then finally, we've got the lone 6 at the end. And so the result of range piped into chunk by is a range consisting of 3 elements, and each one of those ranges is a chunk of the original one. And again, this is entirely lazy, right? It doesn't do anything unless we start iterating over it. So as we iterate over it, chunk by will look ahead to find the next boundary, and then gives you the corresponding subsequence. And it also doesn't do any allocation or anything. Like the subsequences are given to you by like sort of iterator pairs. So chunk by really gives you like pairs of iterators that make up the boundary, lazily as you iterate over them. Now we don't want the actual chunks, we just want the length of them, so we pipe that into transform. So now we're transforming like chunks at a time, and we transform it using the size function. So the result of transform is a range that consists only of the sizes of the individual chunks. And then we've got the numbers we need, and now we just need the maximum, so we use the max function again. And this will give you the length of the longest increasing subsequence. And like chunk by is a bit weird algorithm, like it's a bit weird to wrap your head around, but it's like really, really useful. We're going to use it again in the next problem. The composition shape here is we've got a range, and we want to get a range of ranges. So chunk by, split the range at like borders where they don't satisfy a predicate. There's also at some point in the pipeline, there's an algorithm like chunk on that like does the same, but like at a specific value or something like that. We've got the classic split. This splits the range of a separator. So we've got like list of characters, split on space, which gives you only like splits it in space. Slide, this gives you a sliding window into the range. And that's how you like take a range and split it into a range of ranges so you can process it further. Speaking of words, a classic is reverse words. The input is a string, and the output is a string where all the words, where word is a sequence of letters, are reversed. So if the input is hello world, this is the output. We simply reverse the words, but like keep the overall order of words inside the same. And this is how you can do it imperatively. We iterate over each character. We check whether the alphaness of this character and the alphaness of the previous characters is different than we at like the start of a new word. If so, we have to find the end, and then we reverse it in place. Otherwise, we skip over it because it's not part of a word. And then again, we have to keep track of the previous one. And again, what is the composition here? Well, we want to split the string into words. We want to reverse each chunk of that actually is a word, and then we put it all back together. And this is one pipeline. So we start with our string, and then we use chunk by again. And this time the predicate is, does the alphaness of the left character differ from the alphaness of the right character? If so, one of them is part of a word, and the other one is like the space in between words. And now we've got a list of like the individual words. Again, lazily, no allocation, just subranges into the individual one. We now want to transform those. So we get the chunk, and we know the chunk is a word if like the first character is an alpha character. And if so, we want to reverse it. So we pipe the chunk into reverse. Otherwise, we return it unchanged. And then we're essentially done. We just need to put it into the correct format by joining it back together and like converting it back into a string. And so one difference of functional style compared to the imperative one is that this one like explicitly creates a copy of the result, whereas the other one modified the argument in place. So actually passed the input by value there, so we don't modify the calling argument. The other difference with this problem, this solution, is that it doesn't compile. And it doesn't compile because the lambda in transform, if the if condition is true, it returns a reverse chunk. And if the if condition is false, it returns a chunk. And because the views are lazily, reversing the chunk doesn't actually reverse the chunk. It simply describes this is a chunk that is reversed. And the way it does that is by wrapping it in a reverse view, and this is a different type. So like our if statement returns two different types. And so it doesn't compile. And one way to fix it is to, okay, make it the same type. And the way to make it the same type is to eagerly turn it into the string, for example. And now each chunk is eagerly turned into a string, and now both return a string. But we're having like an intermediate allocation in there. Unfortunately, with standard tools, this is the best you can do. We at ThinkCell have a conditional range. And this essentially does like produces the same type on both ones. That is essentially a view that is internally a variant of the two iterators, and then you iterate over either the actual active one, and this lazily does the composition. I'm planning on bringing that into the standard eventually, because it's like really useful. And it's a macro, right? The conditional range is a macro, so we get like the lazy evaluation. It doesn't really matter here because the actual construction is cheap anyway, but like if it's actually side effects in there, then we use the macro to do it lazily. We use a lot of macros at work because C++ sometimes has this annoying corner cases. But anyways, that is just an optimization. The actual takeaway here is the composition shape, range of ranges to single range. And for that we use join. So join takes a range of ranges and flattens it into a single range where all the elements are back. One after the other. Then there's also join with. This is the inverse of split. It joins it, but adds the separator back in that you passed into split. Now, all of these problems were like pretty obvious range problems. Our input was some sort of range. So about this one. Now the input is a single number x, and the output should be the smallest Fibonacci number that is greater than x. So if the input is 9, then the output should be 13, because the 6th Fibonacci number is 8, and the 7th Fibonacci number is 13. So 13 is the smallest Fibonacci number greater than 9. And I'm going to skip over the imperative version, because I think you know how to do that. More interestingly, I want to look at the composition. Like, what is the composition here? What are the sub-building blocks? And, well, I mean, first step, generate all the Fibonacci numbers. And then the second step, find the first one that is greater than x. So let's suppose we solve the first problem. So all Fibonacci numbers is all the Fibonacci numbers. And then it's just a findif. And if we are smart and generated them in increasing order, then just findif finds the first one, and that is then by definition the first one that's greater than x. Now, how do we actually get all the Fibonacci numbers? Well, we can do something like this. So assuming we've got a function that gives you the nth Fibonacci number, then we first start with a list of infinite numbers using iota. And this simply is a list of increasing integers beginning at the start value. So this is like 0, 1, 2, 3, and so on until, you know. And then we pipe that into transform, and this calls the fib function on each element. And now we've got a list of all Fibonacci numbers. And this is really where the laziness is nice, because this first line doesn't do anything. Right? It simply describes what happens if you start iterating over it. So it describes this is a range that contains all the Fibonacci numbers, but it will not compute anything. Only when the findif code starts iterating over the Fibonacci numbers are they computed one at a time. And because findif will eventually find a Fibonacci number that is greater than x, unless x is like weirdly close to int max, let's not worry about that, this loop will terminate. And then we've got the Fibonacci number. Now, how do we actually implement fib? Well, we can do it like this, declarative Haskell style. If n is 1, less than or equal to 1, then we return it unchanged, otherwise the sum of the two previous ones. And this is like horrible runtime complexity, because we're like exponential blow up of recursion. It's like a really good stress test of like some bytecode interpreter you've written. I have another talk where I just use that as an example to do some benchmarks, because it's not a lot of code that drives really a lot of execution. But we don't need to do it in a functional program style. We can do it imperatively, so we can just write the standard linear code that like keeps track of the last two and then keeps adding them. And I've just threw in a little iota in there to write a fancy for loop that counts from like 0 to n. Now, one problem, and like I know this is not the most efficient one. You can use the crazy linear algebra matrix exponentiation trick or like the closed form formula, which are equivalent. But one problem this has is that like we're using this with transform and iota. So we're first asking for fib0, then we're asking for fib1, then we're asking for fib2. And each time we do that, we start from the very beginning and keep recomputing the same Fibonacci numbers over and over again. This is not very efficient. It would be much nicer if we could reuse all the work we already did. And one very easy way to do that is to use generators. So we can write a function called all Fibonacci numbers that will yield all Fibonacci numbers using a generator. So this is a coroutine. What this means is then that execution can suspend and later resume from within the function. So the way this works is we write this code returning a generator, and every time we want to yield a value, we write co-yield. And this will yield the value to the caller. It's like a return statement, except you can do it multiple times. And then we get our generator and pass it to findf, because a std generator is a range. And now, when we call begin and want to get the first value, we will start executing the function all Fibonacci numbers. Because when we actually call it, it doesn't do anything yet. It's lazily. So the auto generator equals line, it doesn't do anything. Only the actual iteration will start the execution of the loop. And then we will execute it until the first co-yield statement, at which point we will suspend execution, pass the value to the iterator, it's visible to findf. If it doesn't match our predicate, we will ask for the next one, and then execution will jump back to the last co-yield statement, continue from there, compute the next value, go back to the yield, suspend, return that value, and so on. And now we lazily compute all the Fibonacci numbers, but we still remember all the previous states, so we don't have to start over from scratch. And using generators, it's very, very easy to like just sort of do this sort of thing. So the composition shape is here. Even if you don't have a range, you can still create a range, and this might be useful to solve your problem. And simple ones, iota and a transform. It takes you surprisingly far. But for more efficient or more custom ones, you can use generator and co-yield, and then you can just very easily create an arbitrary range of values following some formula. Now, one aside. All Fibonacci numbers, this is an infinite range. I mean, it's not really an infinite range, because eventually we will have integer overflow, which is undefined behavior, so it's not really an infinite range. But I'm chairing the standard committee group that standardizes std ranges. And a couple of months ago, we had a meeting, and we discovered that this code is actually undefined behavior. Because there is some technical words in the standard about how calling member functions on invalid ranges is undefined behavior. And an invalid range is one that isn't valid, and a valid range is one where you can reach the end with finitely many iterations on the iterator. And so every time you have an infinite range, that is an invalid range, and you must not do anything with it, because that would be undefined behavior. And it's a bit of a bummer, because the standard provides infinite ranges. But they're there, but you can't actually use them, because there is no way to use them without causing undefined behavior. So, fun fact, I guess. We're going to fix this eventually. It's just a hard problem, and maybe in 10 years or so, you will be able to actually use them without doing undefined behavior. Because the word is there for a reason. It's a whole thing. Anyways, so the general takeaways here is, when solving a problem, especially one with ranges, try to identify the small building blocks. Listed a couple of ones here. To create ranges, use iota or generator. To transform, use transform and filter. To combine ranges, Cartesian product, zip, and concat are the way to go. To split ranges, so single range into multiple ones, split or chunk by. To join them back together, use join. And then know your algorithms. So like max, min, count, and so on, they're all kind of folds as the technical term, and then the searches. And that way, you minimize the use of for loop. We solved all of those problems without having to write any for loop ourselves. This makes it declaratively, and with the execution policies, you can just have it multi-threaded just by changing one line of code. That's really nice. Now let's look at composing. Yeah, sorry, quick question? Sure. Quick question now and then, yeah, because, yeah.
Wondering whether you looked at the assembly and were sometimes positively surprised by what the compiler generated and sometimes negatively surprised by what the compiler generated.
Yes.
And sort of the second related question is, you talked about laziness.
Mm-hmm.
Can you always be sure that there won't be intermediate materializations? Always sometimes surprised about, sort of parts of these compositions that, materialize themselves?
So regarding the assembly, if you have a benchmark that shows that this particular problem thing is a bottleneck, then yes, it makes sense to look at the assembly, because you've got the abstraction penalty because you use the declarative function programming style. And the optimizer has to see through all that and turn that into imperative code. And yes, this in some situations, the compiler is able to do that, no problem. In other situations, it doesn't matter at all whether the compiler is able to do that because your range has like 10 elements, right? And in some situations, it's not able to do that, and a handwritten version would be better. And then that's fine, right? Then you just have the quick range version and manually replace that with a handwritten optimized version. This is the trade-off. It depends entirely on what exactly you're doing. Right? The other thing regarding the laziness, so by design, they don't like materialize early because the views, they simply create some sort of state machine that only as you iterate over them do they actually drive work. One thing that does happen sort of is the classic example of this if you've got a transform piped into a filter. Then the filter needs to know the transform value in the increment of the iterator in order to know whether to skip it. And then when you get it, the value out of the iterator, you also need the transform value. And what often happens then is that you essentially get the value twice, like do the transformation twice. Like once in the increment to determine, oh, this is a value I want, and then once in the dereference to actually get the value out. And this is sort of caused by laziness because it's too lazy. So it does it every time it's needed, and if it's needed multiple times, it does it multiple times. Right? So this is some potential issue that you run into the laziness. And there are ways to fix it. Usually you want the transform after the filter to make this happen. And there's also like there are some more technical ways to solve it, but yes. Yeah. Okay. So let's look at composing functions more general. This is a function that unsubscribes a user from a mailing list. So we just get the user ID, we look it up, we get its email, we remove it from the subscriber list. And this is a composition of function. We start with a user ID, we turn that into a user, we turn that user into an email, and then we do something with it. The composition chain isn't really written in that order because of the way the expression syntax works. It's sort of like from the inside out, but that's just C++ syntax. But technically, this is function program style using composition of functions. So if you want to be fancy, you can describe it that way. Now, the more interesting thing is, like, what if the intermediate functions can fail? And what if you need to handle that failure locally? So, for example, we've got optional t, and this holds either a t or is empty. And now, what if looking up a user can fail? So the user ID might not be valid, and they might not have a user. Then the composition gets annoying. Because then we call lookup user, and then we get an optional user, and so we need to use an if, and if you have a user, then we get its email, and then we do this. We technically still have a composition chain in there. We start with a user ID, but this time we turn that into a user or nothing. And then technically we sort of turn that into an email or nothing, and if we enter with an email, then we want to do something. But this isn't at all expressed in the code. Like, this is imperative code that describes how to proceed. To make that more declaratively, we sort of want to express the composition chain directly. So given an optional user, how do we get an optional email? Because that's what the composition actually wants. Well, use, for example, the turnover operator, right? So if we've got a user, then we get the email. Otherwise, we return null opt. And this is such an incredible common operation. There's a member function on optional for that transform. I think you had to talk about monadic functions on optional just last time. Who was here last time? Okay, about half. So this might be a bit repetitive, and then it's going to get even more repetitive later on. This is kind of on point, though. So anyways, optional transform has a member function that does exactly this. It takes a function. This function is invoked with the value on the optional, if there is one, and then it returns a different value, potentially of a different types, and unwraps that back into an optional. And so we can turn our optional user into an optional email by directly using transform. And this creates like a member pointer to email and then applies that and so on. Now we've got our optional email. How do we sort of conditionally invoke remove on the subscriber list? Well, using an if, right? If you have an email, conditionally remove that. But we could also be fancy and also get rid of this if by using transform again. And this transform really transforms it into an action. So we take our email and we conditionally transform it into the action of removing it into the subscriber list. And this will only remove the email if the email exists, obviously, because otherwise it can't do it. Unfortunately, this doesn't compile because this would create like an optional void. And an optional void doesn't exist, so we have to do the next best thing and like create an optional monostate. And monostate is essentially just void, except you can put it in containers. Right? It doesn't store any values, but you can store it somewhere. Yes, yeah. So putting it together, our code looks like this. And now we've got a pipeline again. We start with the user ID, turn that into user nothing, transform that into an email or nothing, and transform that by conditionally doing our action. Now, what if not every user has an email address? Well, then if we call user transform, we end up with an optional email. And to handle that, we sort of have two levels of if. The first if is true if we have a user, and the second if is true if that user has an email, and then we need the double star to get the actual email out of there. And this is a bit annoying because we don't really care about the individual failure cases. Like it doesn't matter whether we failed because the user it doesn't exist, or we failed because the user didn't have an email. We want to treat them uniformly. So you can write a function that sort of flattens it back together. And just like we've seen the algorithm to like flatten ranges, we can call this join. Join on ranges takes a range of ranges and returns a single range, and join on optional takes an optional of optionals and returns a single optional. By doing the manual flattening, and this merges the failure cases back together. And this works, but it's like much better, like this works. We can just call user transform and then join. Right? But it's much better if we didn't create the optionality in the first place. Right? And the way to do that is to not call transform, it's to call and then. And then is very similar to transform, except where transform assumed that the function takes a t and returns a u, and then takes a t and returns an optional u. And this means that and then doesn't need to wrap the result of the function back into an optional. Right? So and then we call it with a function that in itself already has failureness built in. Right? Whereas with transform, we call it with functions that don't have failures. Right? So if we call user.endThen the email, then we won't get an optional, we just get an optional. Right? And we lose the information to like distinguish between what exactly failed. But this is what we want. So in this case, the pipeline looks like this. We look up the user, and then we get his email, and then we do the action and we transform it. And one nice advantage of this is that this sort of style makes it very easy to spot which intermediate functions can introduce new failure cases. The ones we call with endThen. Right? The ones with transform, they cannot fail because they can only return a u, not an optional u. I mean, they could still return an optional u, but then we'd have to deal with an optional u down the pipeline. Right? Whereas the ones with endThen, they sort of have failure built in, so they handle it special. Now, what if a user can have multiple email addresses and we want to remove them all? Well, now if we call transform, we get an optional of a vector of emails. And to unpack those, we need an if with a for loop. And again, this is some sort of annoying nesting because we don't really distinguish between an optional that is empty or an optional that contains an empty vector. Right? This is sort of the same case. In either case, we have 0 email addresses that we want to remove. So we want to get rid of this nesting. And one nice way to accomplish that is, again, lots of C++ 26 features in there. Sorry about that. But in C++26, optional t will become a range of 0 or 1. And this means that we can use range algorithm with optional. Because logically, an optional, it's a range, right? It contains 0 elements or 1 element, right? And then we can start iterating over it. And so we can call join the view. And this will take a range of ranges. In this case, the outer range is an optional, so a range of 0 or 1. And the inner range is a range of emails. And it will join it back together. And so if you have an empty optional, then the outer range is empty, so join will be empty. Whereas if you have an outer range of like 1 element, which is a range, then the join will be that range. So this flattens it out, and then we can just use the for each algorithm, for example. But now, since we already started using range algorithms, we can just go all the way and just use also the transform view. So we look up our user, we transform it to get the email, and then we join it. And then we pass that to for each. And this is the same code, it's just be using the transform view instead of the transform member function. And this is semantically equivalent. Transform the member function gives you an optional, transform view gives you like a transform view, but this is still logically a range of 0 or 1 elements. And this pattern of doing a transform and then joining it back together, at some point in the future, there's going to be like a designated view to just do that. Combine it in one, do it more efficiently. And this is usually called flat map in other programming languages, but flat map in C++ is also a data structure, so we have to call it something like transform join. Even though this is sort of exactly the equivalent of and then, right? Because we want to like transform something with a function that in itself can give you like some sort of range, but then we want to join it back immediately. So maybe we can also call this the and then view, because this is exactly the case of and then. But anyways. Now, what if the user IDs are always valid, but sometimes the database isn't accessible? And in that case, we just want to retry it at some later time. And so when we look at the user, we might get a DB error exception. Now, technically, this is some sort of composition, but to really make composition more obvious, we need values, right? The sort of like exception is just some go-to in the middle of the code to the catch block, right? This isn't really a declarative way to handle that. And so we sort of turn failure into exception using expected. Expected is similar to optional. It can potentially hold a t, but whereas optional, when it was empty, it was just empty. And expected, that is empty, holds an error in case. So we have information on why exactly it is empty. And so we change our lookup user function to gives you either user or DB error, right? On success, we get the user. On failure, we get the DB error. And then we can write code like this, now with an if-else instead of a try-catch. Right? So we look up the user. If you have one, we get the email, we move it. Otherwise, we log it and retry later. And now we've got a composition chain. We start with a user, then we have a user or DB error, and then we've got an email or DB error. Except again, this isn't very obvious in the code, so can we make it more obvious? Can you sort of turn an expected of a user or DB error into like an email or DB error? And well, yes, we can, because expected has transform again. Right? So just like with optional, we've got transform unexpected. It takes a t, returns a u, and just grabs it and expected this time. And then it also forwards the error in the appropriate case. So using transform, code looks very similar, but in the end, we get an expected of void or DB error. And when we do the action, expected actually supports void, so we don't need to return the monostate. We can just say transform, and then have it return void, and this will result in an expected of void or DB error. And then we need to handle the error. And again, this is very declarative, because we sort of describe our pipeline, does the operation, and in the end, we've got like one result of the entire operation that we can handle in one centralized place, similar to exceptions. But we can also sort of handle the error in the pipeline style, because there's transform error. Transform error is just like transform, except it's called on the error, right? So this time we pass the value unchanged, and if we've got an error, we invoke the function with the error and return a potentially different error. So we can take in a transform error at the end to handle all errors of all previous states in the pipeline and say, give me the error. In this case, do the recovery, and then because expected doesn't support void in the error case, we have to return monostate again, but it's sort of a good thing because we don't want to silently lose errors along the way, right? And again, similar problem. What if querying the email, again, can fail with a DB error? if we just call transform, we get an expected of an expected, which is annoying because we don't really care about the two errors. Right? We don't care whether it's the user query that failed or the email query. So we can again write a join function that joins it back together, similar code. But it's much better to not do it in the first place. And I think you know how to do that. You call and then. Right? Just like optional, expected also has and then. And just like optional, it assumes the function already has failure built in. So it doesn't need to wrap it in the result. And just like with optional, calling and then makes it really obvious. Oh, this function can fail. But the transform one can't fail because we're using transform and not and then. And then we handle the error at the end. Now, the problem with this sort of error handling using transform error is that the result of this entire pipeline is an expected that is still in the error case. Right? Because transform error just changes the error, but it doesn't turn the expected into a success state. Right? So after all of this operation, the expected is still in the error case. It's just that the error is now monostate instead of a DB error. So it would be more natural to turn the expected into an expected that returns success. And we can't just return an expected that returns success, because calling it with transform, this will result in expected of expected, but this time in the error channel. So now we've got an expected where the value is unchanged, but the error is nested, because we're calling transform, and transform puts in an expected around the result. And we could call join, like write join for the error case, right? But instead we can call sort of a function that does it for you. Do you know what this function is called? Like the and then equivalent for the error. So we've got transform of the value and transform error for the error case, and we've got and then for the value case. And what is the equivalent of and then for the error case? Any guesses? Any guesses from the people that haven't seen the talk a month ago? Yeah, it's not called and then error or something like that. It's called or else. But it's the and then version for the error case. It assumes that the function has failure built in, so it doesn't wrap it. And because the function has failure built in the error case, failure actually means success, right? Because we're doing the wrapping on the like sort of flipped on the error case. So by returning like an optional with success, we can turn the expected into one that succeeds because we've handled the error by using or else. So or else is sort of like the dual to like and then on the thing. The only final nitpick I have of this is that like the monostate that we return in the error case is sort of the wrong type, because it would indicate that this expected can still potentially have an error. It's just that this error is also void. It's empty, but it could still be there. It's much better to use an upcoming type in some standard called no return t. And this sort of means that an error is impossible. Because where monostate contains a single value, no return t contains 0 values. So logically, monostate is like an empty tuple. We don't have any data. Whereas no return t is the empty variant. And if you have a variant that is empty, then you don't have any alternative in your variant. So you can't actually have a variant that is empty. Right? And this is sort of no return t. Monostate is the void in void f empty body. No return t is the void in void abort. Right? Because abort returns void, but it doesn't really return. Right? Like it doesn't return a single value, it returns no values. It will never return. So the return type really should be no return t. And so when the expected of t and monostate is isomorphic to an optional t, because the error can only be like a single value, just like an optional, and expected of t or no return t is isomorphic to t, because the error can only be 0 values, which means you cannot have an error. Right? It's just a more convoluted way of saying t. But this is sort of what we need to do because to stay in the expected world, right? Because or else can't turn like an expected into a non-expected, but we can turn it into expected of t and an error that you can never construct, right? And that's that. And this is really the big downside of expected. The composition works great as long as you have the same error type. So suppose we've got a function query value that given a key returns a string or db error, and then parse value that given a string returns an int or parse error. First of all, what's the return type of the composition? Right? Well, it's an expected of a variant of either one of these errors. But it doesn't compile, because the and then doesn't allow you to change the, you can't really compose them together. You have to like awkwardly cast it into the variant type first, and then the pipeline works. But then at least, no pun intended, you've got the nice way of seeing like, oh, these are the functions that can fail. Only the ones with and then. And the transform one, which just prints it, it can fail. So it would be really nice if expected was inspected like an expected of t and one of multiple errors, and then either starts a t or a variant of one of those errors, and then just automatically accumulates all the failures it's seen along the way. But I will. So the general takeaways of this section is that if you've got optional and expected, you can model optional and failable results, and then you compose them very easily in a functional style using transform to process values, transform error to process errors without actually changing back into the success channel, and then to chain with other operations that can also fail in some sense, and then or else to like chain with an error handling function that actually goes you back into success. But it's like still a bit awkward here. This is where like a pure functional programming language actually has the better tools to handle this. Because sort of like mixing different kinds of failure and optionalness is difficult. Like you can't, if you've unexpected, you can't easily go to optional and vice versa and stuff like that. But if you do that, you minimize use of if. Now, finally, we're almost done. This is a short one. A look at composing I/O. So, in a pure functional programming languages, all functions are also pure. This means no side effects during computation, and they always give you the same value and called with the same arguments. This means no global state, and no functions that interact with the outside world. Because like interacting with the outside world, this can change from the outside, so you don't always return the same values when called with the same input. This raises the obvious question, how do you do anything? Right? If you can't interact with the outside world, like how do you like get some input or whatever? Well, like how do you write a simple function like a program like this that reads an int from the user, squares it, and writes it to the output? Well, you cheat. The idea is you sort of manipulate actions. So instead of having a function readInt that reads an int and gives you that int, you have a function readInt that returns an action that when executed will read an int. Now this is a pure function because it will always give you the same action, the action that will read an int. Actually executing the action, don't worry about that. But like the action, the readInt itself is pure. And writeInt is a function that takes an int and gives you an action that will write that int. Always that action. When you call it with the number 4, you will always get the same action that will write that int. Okay, I mean, we still can't write this function because like when you call readInt, you don't get the int, you get an action. So how do you do that? Well, we can sort of assume that we can like change the value in our action, like sort of like transform it, if we want, right? So we call readInt and we transform it. And we give it a function, and this function will be invoked with the int that we read from the input, and give you an action that will read an int and square it, right? And then we also need to like, and then, because to actually write the int, because if you call transform, then we will get an action that will give you an action that will do something, right? And we want to flatten that, so we call and then, right? And now this function is entirely pure, because when called, it will always give you the action that will read an int, square it, and write it back out. And then our main function, we get the action and run it. Now this is non-pure, right? This actually does like some I/O and stuff. So if you're in a pure functional programming languages, you pretend that everything above the main function is your program, and the main function doesn't actually exist, right? So essentially, your Haskell program, all it does, it manipulates these sort of actions, and then after the Haskell program is done executing, does your actual program execute and actually do all the work that you wanted to do. And this is like a neat trick, so you can still stay in your functional programming world without, having impure code. Now, C++ doesn't need that, right? Functions in C++ don't need to be pure. But like it's still good to like separate I/O from computation, right? Have a computation that takes the input, produce the output without doing any I/O. This makes it much easier to test, much easier to swap out input or output procedures. And like this sort of pattern of composing actions can still be useful to achieve that. So like first declaratively compose the actions, then execute them later. And one sort of big framework that's coming in C++ 26 will use this sort of actions for multi-threading. So we've got this thing called senders, which they're essentially our actions, right? There's some action that will eventually send you some values. And they're meant for like async I/O and stuff, but you can write our like readInt squareInt example. just using senders. So we've got async read int, which gives you a sender that will give you an int, and async write int that will give you a sender that will write the int. And then you compose them using functions, your pipelines again. The then function, this is the transform. It's not called transform this time, it's called then, right? They could have called it map, but that was a data structure, so they called it then instead of transform. And this function let value, this is the end then. I don't know why it's called let value and not end then, because we've called it end then in the other ones, but here it's called let value. Anyways, and then the run action, this means, hey, let's wait for the entire async operation to complete. And this will actually run the action. But it's designed to do multi-threading. So we can write a function do something that takes some sort of scheduler, and then we call schedule, and this declaratively creates an action that will run on the scheduler associated with some thread pool or whatever. And so when we transform it, we do the transformation on a separate thread, right? Something associated with the scheduler. And again, this is declarative, so the first line doesn't do anything, right? It simply composes some actions. Then we can do that again. This time we are again running on the scheduler, computing something else, and this will presumably run on some different kind of thread or something. Then we compose them all using when all. This is an action that will wait until all other actions are done. And up until this point, we again haven't done anything yet. We simply describe some action, and then we say, hey, I'm gonna wait until it's done, and this will actually kick off the work, and now we do stuff once on the thread pool, right? In parallel, we will compute Fibonacci and some primeness, and then we get nice intermingled output because I haven't bothered doing any locking on the output stream there. And you can combine it with the previous example. So we have some functions for async IO, and this time we want to do async read, and then we do some computation. And so we do the entire thing on the scheduler. And this time we use let value because it returns another sender, and this is the end then. So to avoid the nesting, we use let value because this is the end then, right? And then we get our value, so we call fib, we pass that on, and then we call another let value to write it out. And this is some code that will execute some IO, some computation, and some more IO on a thread pool. And because it's asynchronously, while it's waiting to do the computation, the thread pool is not blocked and can do other stuff like other computation. And this makes it really nice to do parallel. Right? Just meant to give you a glance at what's possible with this framework. So the general takeaway here are declaratively build your plans, execute them later, and separate I/O from computation. And that way you minimize impure functions. Now to conclude. We've talked about ranges. Ranges contain 0 or more values. You can call transform to change those values. You can call transform join to change those values using a function that returns a range. And you can call join to flatten nested ranges. We've seen optional and expected. They contain a value or nothing. We can call transform to change that value. We can call and then to change the value in some other way that induces failure. And we could write the join functions that flatten them. And then we've sort of seen the IO actions. They sort of contain a value at some point in the future. Right? It's an action that will give you a value. We can call transform to change those. We can call and then to change the value using another IO action. And we can write a join that flattens nested IO actions. And that all seemed a little bit repetitive. Right? In each of those sections, this is essentially the same thing. And this is because they're all monads. And monads are these huge functional programming thing that's really difficult to understand. But it's not really. It's simply a thing with transform and then and join. And some way to build a monad. And they're really nice. There's some sort of box of some value that can be transformed while keeping it inside the box, so to speak. Right? So we've got an optional t, we can transform it, still have an optional t. We've got an IO action, we can transform it, still have an IO action. And they're so essential for functional programming because they are what enable the composition. Right? And this is why functional programmers talk about monads all day, because they do composition, and monads are the thing that you need to do to composition. And this is really the main takeaway. Functional programming is all about composition, and monads is what enables this composition. And for C++ specifically, write your building blocks using efficient, optimized, and well-tested C++ code, and then compose those building blocks using functional programming. Anyways, again, shout out because we're hiring. So, if you're looking for a new job. And if you like the talk, there's a survey. And then you can also fill in your email if you want to get hired. But you can also do the survey. Thank you.
Stefan. Thank you very much. Very interesting talk. Are there any questions? Okay. Raise your hand again, please.
So you briefly touched on the topic of debugging. What is your experience in actually debugging this in C++?
Yes, so the actual debuggers, if you actually want to start debugging, this is really useful if you're the person that wrote these views and implemented these algorithms. Because the debugger is really useful to find bugs in your implementation of those views. If you just assume that they are correct because they come from the standard library and you want to use a debugger, you're going to have a bit of a bad time. Because, again, this is the abstraction penalty of functional programming. The debugger is meant to work with a different kind of style. Right? So the best way to debug them is to use just print out the intermediate steps in the pipeline. Right? This is my input. I call transform. This is my input now. I call filter. This is my input now. And with C++ 23, let's say, it's really convenient because we've got std print and ranges are printable, so you can just call print, give it a range, and it will print it out, nicely bracketed and all that. So this is the most efficient way to debug those. And it is it works because fundamentally you don't need single-step debugging to fix these problems because you don't have state that you need to watch. You don't need to watch individual variables in your loop because those are all abstracted away. And what you actually want to debug is how does the data transform into those things, and this is then a natural way to debug it. And the good news is, I find myself that when you write code in this way, and assuming you you don't have these sort of bugs where there's a less than, but it should have been a less than or equal, and now the thing doesn't work or something like that, because you have bugs on a more higher level, which is I'm calling a chunk by, but I really didn't want to use a chunk by, right? And on this level, then the printf debugging is the one that's going to tell you how to fix. So it's a different, you approach it in a different way, and so you debug it in a different way because you're looking for errors in a different domain, so to speak. Yeah, but actually don't single step through these things because you will see a lot of standard library code, and it's kind of
Thank you for this very nice talk. I originally had the same question about debugging, but we had someone who implemented all of these expected and so on years ago in our code base, so I'm using them. And, well, aside the debugging, another thing is what if the data that you're interested in is not just a single easy type? Like what I'm seeing in our code base is that we have a lot of lambdas that reference simply everything, and then they modify it outside. So it sounds functional, but it's not functional at all.
Right.
The question is, how exactly would you maintain a bigger context state and still, I don't know, have joy in programming?
Yeah, so if you've got the lambda and the transform, and then the lambda itself references some mutable state, and as you transform the input data, you also change the mutable state in the outside world, then yeah, you're going to have a bad time. And don't do that. It's easy to do, but if you wanna, so for example, the way this happens is so you got some code that's nice, originally written, it takes some values, transforms them, uses the transform values. Very nice. But then while you do that, you also need to count how many transform values you've seen for some other thing, right? And then you're tempted to, I'm just gonna add a increment to my lambda, so as the lambda gets invoked, I'm also gonna count that. The better way is to okay, if I also then wanna maintain a count, maybe, I can use enumerate instead of the input. And enumerate will give you a pair of the index and the element or something. And then you have the running index of the input value that you're dealing with also in the lambda. But without having state, but having it passed in from the algorithm, right? Or stuff like that. Or okay, so I'm going to do the thing and I'm not only going to loop over it, I'm also going to count the values at the end and this sort of thing. And then sort of don't touch the actual data transformation with the statistic gathering that you needed to do, but express that as part of the pipeline. If that makes sense.
Anybody else?
problem that different views return different types, right? So you have that example
Yeah,
that
yeah.
two are not compatible.
Yeah.
Is there a generic form of a container or a wrapper or something that could just take any view and represent it?
Yeah, so right now the generic wrapper that takes any view and represents it is stood vector of T. Right? You can introduce eagerness into the pipeline and create a stood vector of 2. Right? There is in the pipeline, it's going to be in C++29, is like a generic any view. And there's like a type erased wrapper thing that you can do. Like it adds some predictable overhead because now you've got like type erasure in the iteration. And like sometimes it's a bit of annoying because like an iterator operation like consists of like a dereference, an increment, and an equal. So you have like 3 virtual function calls for each step in the pipeline. But like it's there are like some ways to optimize that in special cases. So we're gonna look into that and then give you something like that in like 29. So again, in 10 years you can. Yeah.
I have one more
Yeah.
question, if I may. To my knowledge, C++ doesn't have a concept of purity,
Right.
functional purity,
Right.
Although C++26 has contracts,
Mhm.
will have contracts.
Mhm.
Do you think that's something for C++29 too, or maybe for contracts?
So I don't see adding like a pure keyword or attribute. I mean, maybe an attribute for like optimization purposes. I think somebody want to write a paper like that because C got something like that recently. But like the actual concept of purity isn't like expressed in sort of the language itself. There is some wording in the standard about when the function you call to transform, when it returns like rand or something like that. Right? And then every time you call it, you get a different value. Then this is technically undefined behavior because the standard doesn't mandate in what order it's called and like this sort of thing. So like it sort of requires you to make these functions pure, but unless you read the standard, you won't know that. And, yeah.
Well, thanks. It was a really fun talk.
Thank
to follow.
Okay. Well,
Thank you for the talk. It's more about syntax sequence since you are in the standard.
Mhm.
Is there any easy answer as to why accumulate max were not pipeable? Because I write a lot of them and I like Android piping all the way.
Yeah.
And then we're gonna call rand and then they cannot pipe at the same time.
Yeah, so the specific thing is views are the things that are pipeable. And then the algorithms are like the thing that take ranges and they are not pipeable. But then we've also got 2, which is an algorithm, but it is pipeable. And like range with 3, so like the precursor of the standard one, had pipeable actions, which were like algorithms, but they were pipeable. So a specific reason, no. It's just that's what got imported in the standard. For accumulate specifically, there is going to be in C++29, I think C++29, there is a proposal to add like accumulate as a view. So we'll have an accumulate view that will lazily give you the accumulation values. So the specific one is going to be pipeable in form of a view that does lazy evaluation. So if you want the lazy version of accumulate, you will have that pipeable.
Thank you.
Two-parter.
Mhm.
How many of these views can be made const expert, and given how functional programming or declarative is an abstraction, how much of this ends up being compile time versus runtime?
So how many of the, I think the views are const expert. I think there was a paper that slapped const expert on all of them. Except stuff like, there's a view that reads from an iStream, right? That's not const expert. I think, or did Hannah already get to that one? No, okay. I think the like const expert virtual inheritance was a blocker for const expert iStream or something. Yeah. But anyways, soon they're all going to be const expert for some reason. The like compile time versus runtime, I mean, it depends on your input, right? You can like, if you do the pure functional view composition, then like making it, doing it at compile time is just a matter of adding const expert in the missing places, because usually by design it's const expert because it's like pure things that don't do anything, right? So, but like then like you can use it with both one-time and compile-time values and do the results at compile-time and one-time. Right? Yeah. I think you want to. Yeah. Yeah. In the front.
I generally had a question about like, the outlook of functional programming in C++ and upcoming standards. You already touched it a little bit, so maybe you can share a little bit more thoughts or ideas.
Yeah, so there is going to be a lot of work in like this sort of like area, simply because both ranges and senders receivers are like pretty big functional paradigm thingies. And they're going to get continuous work on. And as part of that, we will probably at some point get like more like utility functions involving lambdas. So if you just want to have like a function to like compose two lambdas very easily, or like to write this sort of stuff, it's going to probably come as some sort of utility drive-by stuff to work better with this pattern.
And then I have a composable question to that. So are you going to, so are there any first how to address this problem about like the performance? Because when you have a good building blocks, but you need to do the functional way.
Yeah, so the actual building blocks, the low-level ones that do all the actual data manipulation, making them imperatively and optimized is a good thing, like the algorithms should be, but then the composition, because like if you do a declare, yes, there might be some overhead, but like you can also make it multi-threaded with a one-liner, right? And if you have imperative code, you're probably not going to bother multi-threading it because it involves like adding stuff to it. So like you get like maybe the ranges code is faster simply because you're able to do it in parallel without some work, right? And then it doesn't really matter. That's like the per core performance would be lower than if you had parallelized imperative code because you don't have parallelized imperative code, right? So.
Thank you very much.
Oh.
Or? Okay, so looks like we're done. So thanks again to Jonathan, Daniel, and Tingsel, and have a nice day.